Welcome to the Boundaries and Behaviors 2 module for Senior Design. I'm Jeff Showalter, and today we're going to be talking about functional representations. Now, previously in Boundaries and Behaviors 1, we focused on abstraction and decomposition. Just as a reminder, abstraction is the concept or idea not associated with any specific form, thereby capturing the commonality of a group of similar forms. In this case, we primarily focus on the function of what needs to be done before we look at the form or how it needs to be done. It allows us to come up with lots of different solutions because we're, again, looking at things at the highest level, so we don't have a lot of requirements that we have to worry about. And it really helps unleash everybody's creativity to kind of come up with some concepts that maybe that they wouldn't have thought of before. Kind of, I guess, in a sense, thinking outside the box. It also allows us to organize the design process, so because we're separating our overall complex system into modules or subsystems or different parts. And then it also allows us to translate whatever the customer needs are into functions. And then once we have those functions, we can figure out a form of implementation for those particular functions. We also looked at decomposition, or reducing things into parts, so reducing something large into a set of smaller subsystems or smaller parts. Basically taking our big problem and making it into a series of littler problems. So some of the tools that we looked at for abstraction and decomposition were black box models, basically taking a functional model of what's going on, black box being kind of the highest level of that particular function, and then looking at our inputs, the functions that need to be performed, and then the outputs. We also looked at function trees. Function trees take our task that needs to be done, or the function that needs to be done, and breaking it up into subtasks. In this particular case here, we had a UAV example where we said, well, one of the things we have to do with that UAV is control how it was flying around. The second one was how we were dealing with different types of fault conditions. And then the last one is managing the data that we get from some of the sensors that are on that particular UAV. If we look at lots of products that have been designed this way, we kind of have come up with a somewhat generic language that encompasses most, if not all, of the different design functions. So we have essentially a vocabulary for functions and a vocabulary for views. So you can kind of look at those two lists, and from them should give you a lot of ideas of the potential functions and flows of your particular system. So this first chart here is a function vocabulary for functional modeling. So if we go from left to right, we start with a class of what needs to be done. Then it breaks it down into some basic functions within that class. If there's any restrictions in that particular class, and then also some of the synonyms or words that we could potentially use in our actual functional models. So here you see the case where we have classes of channels, channeling information, supporting, connecting, branching. This next slide here, provisioning, controlling magnitudes, converting from one form to another, and coming up with some kind of signal. And you see as I move from left to right in each of these cases, I get a little bit more detail as far as what is the function that I'm actually doing. If I look at the flow vocabulary for functional modeling, it works pretty much the same way. We said that we have energy flows, some basic analogies for different types of flows, a specific flow analogy, and then also an effort analogy. And again, if I look at the same thing for materials, which doesn't have kind of as many categories, signals and information does have a lot of those categories. If you kind of just look through all of these, and you see on the bottom of this slide here, we go from the most general categories to increasingly specific as I move from left to right on these particular tables. So another technique, though, that's possible is that we can combine our black box model concept with our function trees using this particular vocabulary. To do this, we typically begin with the black box model and put black boxes within that particular model. Usually the easiest thing is to begin with an input flow and try and imagine how that travels through the different functions of the product. So here are a couple of functional modeling guidelines that will help us create this product. So first of all, we need a functional representation. What's important there is we make sure that we choose where the system boundaries are and use them consistently throughout our function structure. So again, we have to define where does our system end and where does the external environment begin. Some cases that's very clear. Other cases it might not be quite as clear. Then we want to state the different functions in verb-noun form. For example here, we want to be able to import electricity. Then we want to state the function independent of objects in the device. So instead of saying turn gears, maybe we want to say change energy. Then we want to state the functions as device functions rather than user functions. So what is the device doing, not what is the user doing. Then also map prolific functions with a ground symbol and combine any redundant functions that may be part of this particular system. The second thing that we want to do is make sure that we have completeness. So we want to break down our functions into as low of level as possible without using any unnecessary detail to define those particular functions. Then we have to ask the question, do the functions adequately show that we're meeting the customer needs? We also want to ask, do the functions adequately show the flows as they're traveling from into the black box model to the exit of the black box model? And then lastly, we want to make sure that are all of the functions of each component in the product shown. Lastly, what we want to do is do some cross checks. Again, we want to check for conservation of energy and mass and the equilibrium of forces. So basically whatever our inputs are, we should see an output there. We said that's not as important for information flows, but it's definitely important for energy and mass flows. Then we want to verify that each flow has the correct state and type associated with it. And then we want to verify that the functions are in the correct sequence if they're dependent upon each other, and in parallel if they are independent of each other. So let's go back to the example of our Zen model. In our Zen model, the black box model of our Zen waterfall, we want to produce soothing sounds of running water. Our inputs are electrical energy, water in our hand, and on-off information. Our outputs are sound and light, water vapor from water evaporating from the water that's running through the system. And we don't keep our hand in the system. We basically turn it on or turn it off. So we return our hand to the owner. As far as the on-off information, potentially that could be something like just like an LED or a light that lets us know if we've actually turned our system on or off. So what we're going to do here now is fill in the black box for this particular case. So my input was electrical energy, so I have to accept that electrical energy, transform it from one form of electrical to another, then transmit that new electrical energy within the system and use it to control our electrical energy. All right, so being able to control the electrical energy, basically turning it on and off, I need to have a hand that does that for me. So I have a separate input where my hand goes into the system. The system accepts the hand, and then it gives the hand back, so it gets returned to the owner. Once the system has been turned on, then basically we want to transmit that energy, divide it up into a number of places within the system, be able to transmit it to a spot where we're going to be able to transform that energy from electrical energy to optical energy. Obviously the system has some lights as part of it. We also then want to be able to transform the electrical energy to mechanical energy, basically a pumping system. And believe in this particular case we're also using heat energy. So then once we transform the water to heated water, basically transfer that water into the system. Okay, then we can use gravity as an input, potential energy, and be able to convert that energy and eventually release the water, guide that water from one tray to another, eventually discharge the water into some pool, and then also convert some of that potential energy to sound. So this particular system, one of the big benefits of the system is to be able to hear that trickling water. So converting that energy to sound is a big part of this particular system. So it looks like we're almost done here. We have a couple of other items here. Obviously the water is another input to the system. The system has to accept the water, store the water, filter the water, and then put it into the transfer system. So again, that's not a main part of the way that the system is going to be working, not the main function of the system, but it is another function that has to be performed on startup of that particular system. So again, it's important to think about not just when the system is normally operating the way that it's supposed to be operating, but also what are some of the things that need to be done up front before the system is ready to go, and then afterwards what we're going to do with it once we're done with the system. So basically one of the things that we want to do is check the validity of our functional representation. So we want to make sure that the system boundaries are carefully chosen and we use them consistently. We want to make sure that all functions are in the verb-noun form. We also want to make sure that all functions are independent of objects in the device. So we want to make sure that we don't imply that things are being the implementation of how we're doing things, just that we're performing certain functions. We want to try and make sure that the functions are device functions and not user functions. In some cases that's not always possible. Slide says here that if it's unavoidable, use a double box for that particular function. And then we should be able to potentially map prolific functions to a ground symbol. So in that particular case, something will only be shown once. And then we also want to make sure that we combine redundant functions. We don't want to have the same function in three different places. If we're performing the same function in three different areas, we would just want to have one function and have three inputs and three outputs. We also want to check the validity of the system for completeness. So in that particular case, we want to get as low a level as functions as possible without making the thing overly detailed that we really can't tell what's going on at all in the system. We want to make sure that the functions adequately show that we're meeting all of the customer's needs. We also want to make sure that the functions adequately show the flows traveling from the input to the output. And we also want to make sure that the functions of each component are in the product shown. So we want to make sure that everything that we're saying is there is actually there. And then lastly, we want to just do a cross check. So we want to make sure that our conservation of energy and mass and the equilibrium of forces is balanced. We want to verify that each flow is of the correct type and of the correct state. And we also want to make sure that if the functions are dependent upon each other, that they're in series, and if they're independent of each other, basically that they're in parallel. So now that we have this model, what are we going to do with it? Well, we can focus on the functions that are really important to the operation of the device. We could potentially formulate new ways of doing the same thing. If we know the general functionality of things that need to be done, how we're going to implement those is going to be pretty much up to us. We want to identify functions and flows that may not have been originally considered. Maybe there's some things that we forgot. Maybe there's some things we left out because we said that's too much detail, but maybe it actually is really important to the operation of the device. And then we want to be able to develop modules that we could be used across different products. So if we're performing the same general function in 3 different products, maybe we can use those same modules in each one of the products. And then lastly, we want to be able to compare to other products and solutions that are out there and kind of see how well your particular idea stacks up with somebody else's idea. So this concludes the module on Boundaries and Behaviors 2. Good luck in your senior design projects, and we'll see you next time.